Okay, so hello everyone. Welcome to our video in Abstract Algebra. And today we're going to talk about some preliminaries of Abstract Algebra. So we're going to talk about first about equivalence relations. So in mathematics, things that are considered different in one context may be viewed as equivalent in another context. For instance, we have already seen one such example. Indeed, the sums of 2 plus 1 and 4 plus 4 are certainly different in ordinary arithmetic, since 2 plus 1 is equal to 3, obviously, and 4 plus 4 is equal to 8. But they are the same under modulo 5 arithmetic, since we're in modulo 5, remember, in modular arithmetic, we're only focusing on the remainder. So if we're going to have modulo 5 here, the remainder is 3. If we're going to have 8 modulo 5, the remainder is 3. So indeed they are correct, or they are the same. In such a way that if we're going to write 3 modulo 5 is going to be equivalent to 3 itself, and 8 modulo 5 is going to be equal or equivalent to 3. So hence they are equal. What is needed to make these distinctions precise is an appropriate generalization of the notion of equality. That is, we need a formal mechanism for specifying whether two quantities are the same in each setting. We call this mechanism an equivalence relation. So definition 1.10, equivalence relations. An equivalence relation on a set S is a set R of ordered pairs of elements of S such that, number one, for any ordered pair A and A, AA in R, for all A in S, we call this reflexive property. So whatever we have in A and A, which is in R, it will be true for all A and S. Okay, so that will be our reflexive property. Number two, for A and B, which is in R, it implies that B and A is also in R, which is symmetric property. So again, if we have A and B in R, therefore it is just equal of saying it implies that B and A is also in R. For number three, um, A and B is in R and B and C is in R. It implies that A and C is also in R. So that's your transitive property. When R is an equivalence relation in a set S, it is customary to write this notation instead of A and B is in R. So, for number one, if we're going to make use of this notation, so A is related to A, that's reflexive property for all A and S. For number two, if A is related to B, it implies that B is related to A, that's symmetric property. For number three, if A is related to B and B is related to C, therefore we say that A is related to C. So that's how we use this notation right here. Also, since an equivalence relation is just a generalization of equality, these symbols, 1, 2, and 3, are usually used as well. So we have equivalence relation still. Also, since an equivalence relation is like that, the same thing, using this notation, the three properties become A is related to A, that's reflexivity. A is in B, or A is related to B, implies B is related to A, that's symmetry. And A is related to B and B is related to C, therefore B is related to C, that's transitivity. If this symbol is an equivalence relation on a set S and A is in S, then the set of all A, the collection of all A's here, which is equal to X in all S, such that X is related to A, is called the equivalence class of S containing this element A. So an example, let S be a set of integers and let n be a positive integer. If A and B is in S, define that A is congruent to B if A mod n is equal to B mod n. So that is if A minus B is divisible by the modulo n. Then this equivalence relation, this uh, congruence is an equivalence relation on S, and this collection of A is equal to A plus Kn, such that K is in the set S. So this is an important example. We're going to provide a proof for this, that this really works. Certainly, A minus A is divisible by N, because it will be 0, so 0 is divisible by any number, so that A is congruent to A for all A and S. Next, assume that A is congruent to B. Say A minus B is equal to R times N. So we're going to set a minus b is equal to r times n, since a is in this form. So we're going to make it like that. Then b minus a is going to be equal to negative r times n, since we have shifted, or we shifted a minus b, became b minus a. So one symbol from the right hand side shall also be changed. So we say we're going to change the symbol for r to be negative, or the sign rather for r, and hence b is congruent to a. Finally, assume that a is congruent to b and b is congruent to c. Say we have a minus b is equal to rn, as we have given above, and b minus c is equal to sn. Then we have a minus c is equal to a minus b plus b minus c. Okay? And that will be equal to, just substituting, a minus b is rn and b minus c is sn. So we have rn plus sn, we're going to get the common factor, which is r plus which is the common factor, which is n rather. So r plus s times n. So we therefore say that A is indeed congruent to C. Okay, so that's one example for equivalence relations. Next is we're going to define what a partition is. That's definition 1.11. A partition of a set S is a collection of non-empty disjoint subsets of S whose union overly, if we're going to get the general union, is also equal to S. So example below is a partition of a set into four subsets. So we have this. This is one set. This figure here. They are divided or partitioned into four sets. So we have first, second, third, and fourth sets. So notice, if we're going to get if we're going to collect the non-empty disjoint subsets of S, the union is going to get back to S. So that's what we call partitioning. So after that, define definition 1.12, functions or mappings. Definition: a function or a mapping, phi, from a set A to a set B is a rule that assigns to each element A and A exactly one element of B and B. Okay, so the set A is called the domain of phi, and B is called the range of phi. So if phi assigns B to A, then B is what we call the image of A under phi, which is the function. The subset of B comprising all images of elements of A is called the image of A under phi. Okay, that is big A rather. So further, we use the shorthand notation um, phi is a mapping from A to B to mean that phi is a mapping. Well, that's what I said. So we will write phi of A as equal to B, or phi is a mapping from A to B to indicate that phi carries rather from A to B. Then we're going to talk about, after that, well, we're just done about the functions or mappings. We're going to talk about composition of functions. That's definition 1.13. So let phi be a mapping from A to B and psi be a mapping from B to C. The composition of phi times psi is a mapping from A to C defined by phi and psi. Phi times psi of A equals phi times this, psi times the phi of A for all A in big A. So the composition function of psi times phi can be visualized as shown below. So we can see it's composed. So first we have an element A. We compose that with our phi, which is going to be phi of A. And then this new function here will be composed into by psi. So that's going to be psi of phi of A. So in short, A is composed by phi and psi. But first, psi first, and then phi. Further, in calculus courses or also in algebra courses, especially in elementary and beginning algebra, the composition of f with g is written as f of g. So this is how we write it down. So f of g of x, and it's defined by f of g of x equals f times g of x. So which is our common notation for composition of functions, especially in basic algebra. Definition 1.14, we're going to talk about one-to-one function. Definition: a function phi is from a set big A is called one-to-one if for all a sub 1 and a sub 2 in big A, phi of a sub 1 is equal to the phi of a sub 2, which implies that a sub 1 is equal to a sub 2. So that is what we have as a one-to-one function. So phi is one-to-one here because for every element a sub 1, it will give us a phi which is a sub 2. And for every element a sub 2, it will give us an element which is in the range of phi a sub 2. Rather, a sub 1 gives a mapping of phi a sub 1. This is psi. Say we have a psi, and psi gives us a sub 1, which is psi of a sub 1, and a sub 2 gives us an image of psi of a sub 2, which is they are equal. So this example is going to be not 1 to 1. Okay. Definition 1.15, functions, a function from A onto B. So a function phi from a set A is said to be onto B if each element of B is the image of at least one element of A. Again, if each element of B, big B, is the image of at least one element of A, of big A. In symbols, phi of A, phi of a mapping from A to B is onto if for each set of B and big B, there is at least one A in big A such that the phi of A is equal to B. So, for example, here, this is onto. So, notice that in every element in phi here, it gives us a mapping in B, which is actually, this is many to one in our common understanding. So this is many to one. So for instance, this element here and this element here, it gives us a single outcome, which is A, for example. 2 gives us an outcome of B, and 4 gives us an outcome of C. So in short, when you say onto, it's simply many to one. This is not onto, all right? Since what do we have here? There are two. So this one doesn't have any doesn't have an image. It doesn't have a pre-image from this set A. So it should be that each element of B is the image. So there's no image for this. So this is not onto. Okay. Next, we're nearing the end of this video. So we have Theorem 1.16, which are properties of functions. So given the functions alpha, which is a mapping from A to B, beta, which is a mapping from B to C, and gamma, which is a mapping from C to D, then number one, it displays associativity. Gamma times beta times alpha, which is a group, the grouping is beta and alpha, is equal to the group of gamma and beta times alpha. So that's associativity. Number two, if alpha and beta are 1 to 1, then beta times alpha is 1 to 1 as well. If alpha and beta are onto, then beta times alpha is onto as well. Number four, if alpha is 1 to 1 and onto, then there is a function inverse of A, or A inverse. We called it like that, or simply it's A raised to negative 1, but we like to call it A inverse from B onto A, such that A inverse times, sorry, this is not A, alpha rather. Alpha inverse times alpha times A is equal to A for all A in big A, and alpha times alpha inverse times B is equal to B for all B in big B. So to display a proof for only part 1, the others are given as an exercise. Let A be in big A, then gamma times beta times alpha is times A. We're gonna move A inside, so we have gamma times the quantity of beta times alpha times A, and we're going to move further A inside, so gamma is equal to beta, which gamma of beta of alpha of A. So we can see that this connection wherein A goes deeper and deeper to be beside alpha. On the other hand, on the right hand side, gamma times beta times alpha is equal to A. So we put A inside, we put it beside alpha first, and then we put it inside. So the thing is, looking at these two last parts, we can see that they're equal. Hence, gamma times beta times alpha is equal to gamma times beta times alpha. So you can see the grouping, which is different. So this proves as associativity. Okay, so that's the end of the slide. Thank you very much for watching. I hope you have that concepts of abstract algebra for certain. And we're going to talk more about groups in the near future. So thank you very much for watching.